So greetings to all. Today, myself, Bhavyan Sharma, 19BCE1282. I have gotten the topic SHA512, and I'm here to give a presentation on the topic. So first of all, what is the requirement of hash functions? So whenever we do something, there should be a need for that. So the requirements for a hash function is it should be applied on a message that can be of any size. Second thing is it should produce an output of fixed output length of h. It should be easy to compute h equal to hm for any message. It shouldn't take much time to compute the hash algorithm, which gives us the output as hashed. So given a hash value h is infeasible to find y such that h of y is equal to h. That is, uh, let's suppose that the message that I want to hash is hello. So now the output or the hash that I get from inserting my message here in this function hash, uh, it should be computably infeasible for me to decode it back, or uh, you know, for a hit and trial also, it should be very difficult for me to guess this edge so that after putting into this hash function, I get the same output. This is the one way property. That is, I can hash my message, but I cannot get my message back from the hash value. For given block X, it is computational infeasible to find y is not equal to X with h of y is equal to h of X. That is, for two different messages, it should not give me the same value. Hello and world are two different words, but their hash shouldn't be the same. If their hash is coming to be same, then there would be many such messages which would uh, result in the same hash value. This is called as the collision resistance of a hash function. It should not happen. Third is, it is computationally infeasible to find messages M1 and M2 with HM1 equal to HM2. So as we discussed earlier, just right now, that it shouldn't have collisions. So this is an example of a simple hash function. In this simple hash function, the input is the message or file or anything that is to be hashed, and it's viewed as a sequence of n-bit block. So how it is done is, if you want the value of ith hash, the ith bit value of the hash, then you have to take XOR of ith bit of every block. Like if there are 1024 bits in every block, then my hash output would also be of length 1024. And for the 1024th bit, I would take every bit of every block, 1024th bit of every block, and XOR them. And whatever the result I'll get, it would be the ith or the 1024th bit of my hash value. So now, where does SHA512 comes into the picture? So the algorithm takes as input a message with maximum length of less than 2 to the power 128 bits and produces as output of 512-bit message digest. So see, with these many bits and 512-bit message, you can imagine uh, how the encryption is going on. Like 512 bits is a huge number to compute. That's why it is both collision resistance and also uh, it provides a very good security. So the input is processed into 1024-bit blocks of each size. Like if I have, uh, uh, let's say 2048 bit message, then it would be divided into 1024 bits block. So 2-bit block would be there and they would be processed parallelly. So this is the process, and we will understand it. This is the process how SHA-512 encrypts or hashes a message. So as you can see here, this is our message which contains L bits. Now we are padding it so that it comes in the form of n into 1024 bits. This L, you must see here, this L is 128-bit size, which contains the length of the original message. This was the length of the original message, and we padded it with these ones or zeros, and this L contains the length of the original message. So first, we have to pad the message like this, and it should come in the size of n into 1024 bits. Now, what we do is in the next step, the next layer, we divide this message, this huge message, into blocks of 1024 bits size each. This block is also 1024, this is also 1024 bits, and so on. We get mn blocks. Now, for each block, we will see how the hash is being calculated. So here, we have taken a hash function, and this hash function is of size 512 bits because the output of SHA-512 is 512 bits. Now, this is 512 bits size. This is a special round function which we would see in a minute. And then this round function gets input from a random hash here of size 512. It takes the message and then modulo it and gives us an output of size 512. Now this hash value that we have uh, uh, that we got here is further used to calculate hash of other message blocks. Now we won't use this hash value, but use this h1 to calculate further round function and then modulo each message block. And doing it would result us in the final outcome, that is the h of n. That is our final answer of the hash value of this message. So the output would be hn. It would be of size 512 bits. And this is the process. We first divide it into blocks and then take a hash value, then process it into the round function, modulo it with the message, and then get h1. And this h1 is then used in the round function of another message block. So it goes on like this, and in the end, we are left with the final result, that is hn. So these are the steps. Append padding bits. The message is padded so that its length is congruent to 896 modulo 1024. So dividing the blocks into 1024 length, it is done like that. Because 896 is why 896? Because if you would have seen that 128 is also added, so 896 plus 128 gives 1024. So this is the logic behind it. Padding is always added even if the message is already of the desired length. So this is one of the property. Thus, the number of padding bits is in the range of 1 to 1024. The padding consists of a singly 1 bit followed by the necessary number of 0 bits. Here also, we have seen that 1 and the rest of the padding that we add are of zeros. Step 2, the append length. The L that is shown here is the length of the original message. So this block is treated as an unsigned 128-bit integer and contains the length of the original message. Initialize hash buffer. This was the initialized hash buffer. Now, to understand this initial hash buffer, there are some properties in it. So the properties is this 512-bit buffer has 8 64-bit registers, that is A, B, C, D, E, F, G, and H. Now, these 8 64-bit registers make one 512 initial hash buffer. And this initial buffer is initial hash value is used to encrypt all the messages in sequence. So the outcome of the first two steps produces a message that is an integer multiple of 1024 bits in length. The expanded message is represented as a sequence of 1024 bit blocks M1, M2, and Mn, so that total length of expanded messages n into 1024 bits. Now, this is what we saw, the round function, the f in here. This is the round function. So what we do in a round function is, this is a message schedule, and this is the initial buffer that we get. And as you can see, it has subparts A, B, C, D, E, F, G, H, each of size 64, and this being of bit size 512. Now what happens is, we get this. This is a random generated value k. This is a random constant generated value. Here also it is random, here also it is random, here also it is random. And what it does is, it would take a message, and then with the help of this randomly generated k0 and this buffer, we would calculate round 0, and then this round 0 is used to calculate the round 1, and so that it reaches round 79. After that, for the last round calculation, there is a difference between how we calculate round from 0 to 79 and the last round, that is 80 round. There are total 80 rounds. So how we calculate the 80 round? So what we take is, we take the final round as input, and we take the original, that is A, B, C, D, E, F, G, H, 8 buffers, original 8 buffers, and the last rounds output. And then this is not XOR operation, this is modulo operation, and then we modulo it, and we finally get the hash function, hash value, and this is the final result. So what we do is, for the round 79, we calculate for each round with a random value, and then keep on doing it until round 17, until round 80, in which we take the output of round 79 and the 8 buffers of the original hash, and then modulo it to get the final output. So SHA512 processing of a single 1024-bit block, as I explained, using that diagram. Each round takes as input a 512 buffer and updates the content of the buffer. Add input to the first buffer. The buffer has the value of intermediate hash value. Each round T makes use of 64-bit value WT derived from a current 1024-bit block being processed. The output of the 80th block is added to the input of the first round to produce HI. Output of the message is 512-bit message, and this is how, for each round, we are calculating the values of A, B, C, D, E, F, G, and H. So you can refer this diagram. Actually, the processing that happens behind it is very mathematical, and it would take a lot of time for me to explain. But with the help of this diagram, it would be easy for you to understand that what is happening. So now coming to the applications of SHA512. So 512 hash algorithm is very secure and very encryptive by nature, and it's also being used in protocols including TLS, SSL, PGP, and SSH. keys. SSH is widely used by GitHub, and you have to SSL also is used by GitHub, and SSH is also being used by GitHub. And SHA512 is a part of the system to authenticate archival video from the International Criminal Tribunal of Rwandan genocide. So this is also an application of SHA512. So that's it from my end. Thank you, and I hope that I made myself uh, clear and presented whatever I wanted to in a good way. So thank you.